Alrighty, I think it's time to go ahead, get started. So first of all, let me welcome you to this CNCF webinar, Stateful Workloads and Kubernetes, a Gnarly problem or an awesome opportunity. My name is Christian Jans. I'm a CNCF ambassador and cloud consultant for various companies, and I'll be moderating today's webinar. First of all, thanks everyone for joining. It's a pleasure to have you here. And also, please let us welcome our presenter today, which is Partha Seetala, who is CTO at Robin Systems or robin.io. As a little input, you will not be allowed to speak or talk as an attendee during the webinar, so you're muted. There is a Q&A button at the bottom of your screen, so please feel free to drop your questions in there, and we will answer as many as we can once the presentation is over. Very important, try to use the Q&A button because if in the chat we might lose the information. The session is being recorded and will be sent out afterward along with a link to the presentation. And with that, thanks for joining, and I'll hand it over to Partha to kick off the presentation. Thank you.
Thanks, Christian, and hello everyone. As Christian mentioned, I'm going to be talking about some of the challenges that one would face if you're trying to run complex stateful applications on Kubernetes. And then I'll follow it up with what are the potential solutions to address those challenges. So let's start with an obvious statement, right? I mean, Kubernetes is a great platform. It's a wonderful platform with a lot of primitives that help the deployment as well as the lifecycle management of stateless workloads. Now, imagine that if you could take this platform and then you're able to run stateful workloads on it. And when I say stateful workloads, I'm not talking about any workload that requires a persistent data volume. I'm specifically referring to the ones which are heavy hitters, right? Things like big data platforms such as Cloudera's, Hortonworks, or NoSQL databases such as a sharded replica set-based MongoDB. We're talking about production scale deployments of Mongo, Cassandra, Couch, or even more complex RDBMS solutions like Oracle RAC, right? Splunk, SAP HANA. Now, these are the workloads that you typically do not associate with Kubernetes. But imagine that if you could actually run them on Kubernetes, right? So what is the power of that? Now, obviously, these workloads are data-heavy workloads, which means that you need to have a very strong persistent story around that, as well as they are networked because they are distributed databases. So you also need to have very strong networking components, right, to enable these workloads. And if you look at the state of the art right now in both networking and storage, there are about 27 storage vendors who are CNCF certified to provide storage for containers today, right? And there are about 21 vendors that provide CNI plugins for Kubernetes. So in a way, if you look at it, you might appear that it's a largely. Can you see my screen? It looks like there's a chat window. Okay, I think it might be resolved. All right, let me continue. If somebody cannot see my screen, my slides, then please do type in the chat window so that we can figure out if there's anything wrong. Or anyway, so coming back to this, right? I mean, there are so many vendors providing storage and networking, right? So it almost feels like it's a solved problem. So what is there remaining to be done, right? Especially with Kubernetes itself introducing things like stateful set, persistent volumes, persistent volume claims, snapshot contents, and things like that, right? Now, there was a survey that was done by CNCF, and the survey was essentially to find out what are the most complex challenges that people face with Kubernetes today, right? But despite so many vendors providing storage and networking, there are 48% of the respondents who said that storage is still a very big challenge, and almost a similar number said networking is still a big challenge. So the question is, why is it that with so much of vendor support, it's still difficult for many people to run complex stateful workloads on Kubernetes, right? And that is going to be the bulk of my presentation today, the challenges, as well as I do want to also end with solutions, right? But before all that, right, what makes me a subject matter expert on talking about this topic? So just as a way of introduction, again, my name is Partha Seetala. I'm the Chief Technology Officer of Robin Systems, robin.io. And prior to that, I was a distinguished engineer in the storage division of Veritas Symantec. And I had the good fortune of spending several years building multiple products in distributed storage, big data, and data analytics space. Now, when it comes to Robin itself, we are about a 4-year-old startup based out of Silicon Valley. And what we have done is that we have built a software that runs alongside Kubernetes, and it's a software that enables the deployment as well as the lifecycle management of these complex workloads, right? And just as a kind of proof, so before we get into the more depressing, what are the challenges part, let me just give you hope about what is possible by actually highlighting some of our current customer deployments that showcases what is possible with Kubernetes today, right? So I've showcased 3 different large customers here. It's a variety of different workloads. The first one is a security analytics pipeline. It's a very massive ingest that happens, about 11 billion security events every single day into this pipeline. It runs Elasticsearch, Logstash, Kibana, Kafka on Kubernetes, enabled through Robin, through our storage and all the innovations that we bring. I'm going to talk about that later. Then the next one is, again, an analytics company that is running a Cloudera, Impala, Kafka, and Druid-based data analytics pipeline. Now, again, look at this, right? We are actually running a 6 petabytes Cloudera cluster on Kubernetes. This is something that is it's typically unheard of, right? Typically, when you look at stateful workloads today on Kubernetes. And just for variety, right? The last one is a very large travels company, and they run about 400 Oracle RAC database clusters. And that's, again, a very interesting thing, right? Running Oracle RAC on Kubernetes, right? So clearly it can be done, but there are several challenges that one needs to overcome. So let's get into that, right? What are the challenges? Now, I've broken up the challenges because in our journey, right, we have actually encountered many of these challenges, and we have built solutions that essentially overcome those challenges. But those challenges themselves fall into 4 categories around storage, networking, general CRI or container management, as well as some of the general Kubernetes challenges themselves. So let me dig a little deeper into that, right? Let's start with storage. Now, CSI is, of course, now GA. 1.0 is now available. Everybody gets to use it. And if any storage vendor tells you that providing persistent storage to pods is a big problem, then I think they are lying. Because with CSI and with such a large vendor support, if all you want is providing storage to pods and ensuring that that storage is available when the pod relocates or crashes, that is a largely solved problem, right? So the real challenges that you'll face when you're trying to onboard complex applications are about 4 of them, right? At a very broad level. So the first one is, many of the databases will require data management that goes beyond just providing storage, right? And when I say data management, things like you want to snapshot your database, you want to clone it, you want to back it up, you want to restore, or you want to migrate it from one cluster to the other. And why is that a challenge, right? Because obviously, storage-based snapshots has been in the industry for 30 years, right? Adapting that to Kubernetes is just a matter of time, and it has been done by many vendors, right? So why is data management a challenge? So a couple of reasons for that, right? Number one is, even with the CSI's introduction of the snapshotting capabilities, it's still at a per volume basis, right? But when you look at a distributed database, let's say a Mongo database or even Oracle RAC and all that, right? They are partitioned, they have multiple instances running. And when you take a snapshot, to be application consistent, you actually have to create a consistency group that spans not just one volume, but all the volumes across all the shards of your database. Now that's where you start to see some challenges. How do you essentially coordinate and create an application consistent snapshot that spans multiple partitions, multiple disks, multiple nodes, and so on, right? So that's the first challenge that needs to be overcome. Because without data management, running a database is just going to be a toy deployment. You've got to have that to be able to run it in production. The next one is around data placement. Kubernetes actually has a very great orchestrator. It's a highly flexible orchestrator that you could program and then influence. But when you look at complex workloads such as, let's say, Hortonworks or Cloudera or Splunk and things like that, right? They have certain constraints and they have certain built-in assumptions around how faults are going to be tolerated by the workload itself, right? And they also have certain constraints around how performance needs to be handled. For example, if you're running a Hadoop distribution, right? One of the common asks is, can I get data locality? Because you would want to minimize the network traffic across racks and things like that, right? So how do you influence data locality when you're doing pod placement, right? So that's a challenge, because clearly Kubernetes scheduler by itself does not have the primitives to do storage-based scheduling, right? That's resides outside, provided by the CSI driver, right? So that's one thing. The next one is around data placement, not just for data locality, but for things like affinity and anti-affinity. For example, if you look at Oracle RAC, right? So it's a great example because it's a distributed database, highly transactional. It has its own notion of how to evict nodes or how to figure out when there is a split brain and things like that. And it relies on disk-based heartbeats for that, right? So there's a voting disk and all that stuff, right? And typically, when you deploy an Oracle RAC, you want to ensure that not just at the pod level, but at the storage level, you do not co-locate your voting disk volume with the data volumes for Oracle RAC, right? So how do you influence that in a Kubernetes scheduler when those things are not available, right? So that's the other challenge that you'll have to run into or overcome. So third one is kind of interesting, and I think this is a must-have if you're trying to onboard many of the complex workloads, and that's around the management of changes that happen to a root file system. Now, clearly, when Docker came about, it advocated a philosophy where the root file system is supposed to be maintained stateless, right? Obviously, because Docker reconstructs that when you bring up a container. But many of the workloads that we're talking about predate both Docker and Kubernetes, right? And for them, they sprinkle state all over the place. They sprinkle states in etc directory, /var, / whatever it is, right? And if you reconstruct that upon pod failure or container failure, then the application really cannot adjust to that, right? And these applications, as I said, they predate Docker, and so it essentially means that they cannot change very easily to completely adhere to the Docker philosophy, right? So you really need to solve this problem more holistically. So any changes that an app makes to the root file system of the container needs to be preserved when the container is relocated to a different host or it is restarted. And finally, the one cool thing about Kubernetes is that it allows you to consolidate your workloads, right? If you take beefy servers and then you want to run multiple databases on that, you're essentially putting multiple databases on the same physical host, right? This is a great benefit, but with it comes a bunch of operational challenges, right? Let's say you're running multiple, let's say Mongo shards on the same host, right? Now, each one is running a massive query load or whatever it is. So there is no predictability of the query performance because one database shard could essentially load up the entire disk or the host and taking down the performance guarantees of the other one. So it is very crucial to enable guaranteed performance SLAs when you are trying to onboard data-centric workloads onto Kubernetes. Right? So those are the 4 storage challenges that we saw and our customers saw when we were enabling them to run these workloads, and these need to be addressed. So now let's move on to the next one. Right? So this is a storage one. Let's look at the next part of it, right? CNI. Again, CNI, there are quite a lot of providers, 20 such CNI providers, I think 14 plus security providers. I think the service mesh is making it incredibly easy to do many things today and all that, right? So what are the challenges? So a couple of things here, right? So I'll kind of highlight 3 challenges that we had to overcome to enable things like SAP HANA and Cloudera and all that to run on Kubernetes. So the first one is around how Kubernetes makes IP addresses ephemeral, right? Even with stateful sets, when a pod is assigned an IP address, it is not preserved when the pod moves, right? Or a pod, and technically in Kubernetes, the pod doesn't move, but when the pod, like let's say, started again, right? It gets a completely different IP address. This is actually not a problem for majority of the born in cloud or very cloud native workloads. But when you go to the older workloads, they have essentially made assumptions around how IP address and host name binding remains static. They might put that information somewhere in their configuration database or somewhere, right? And if you don't preserve the IP address persistency upon pod relocations, then it's a pretty big mess, right? And those workloads essentially see that some partitions of your workload, the pod, for example, right, has been evicted from the cluster and it rejoined back and something new rejoined back, right? So those are the kind of inconsistencies that you'll start to see, right, which break the correctness of your application. So that needs to be addressed clearly. The next one is around the ability to connect multiple NICs to a pod. So why is that important? So complex workloads that specially require data rebalancing or data rebuilds and things like that, they ideally would like to separate the client traffic, which is the north-south traffic, from the east-west management traffic, or the data rebuild or data management traffic, right? And ideally, it's best done on 2 different NICs, 2 different L3 subnets connected to 2 different switches and all that, right? So that's again a challenge with this traditional CNI framework that Kubernetes has. You got to enhance it a little bit to get multiple NICs. And finally, one challenge that we found was around connectivity to a workload that is running on Kubernetes by clients that are completely outside the Kubernetes network, right? Now, traditionally, that's solved through the port mapping or those kind of primitives in Kubernetes, the ingress routes and whatnot. Not all of them work with workloads such as Cloudera and all that, primarily because many of these workloads have their own UI and they embed like host names and IP addresses in the URLs within the web page, right, or within the HTML. And that makes connectivity to pods from outside a little harder if you're navigating to the pod through the web UI of that workload. Okay. All right, so that's on the CNI and CSI challenges, right? So the next one is around CRI, right? And this is kind of strange because when Docker is everywhere, everybody knows how to build a Docker container. And pretty much every vendor is now building out a Docker container for their software, right? So what else needs to be done, right? I mean, it obviously feels like it's all a solved problem. So when we were running these workloads, we ran into about 4 such challenges and on the CRI that had to be handled, right? So the first one is around, let me just expand all of this. The first one is around the fact that Docker shim, which is the default CRI for Kubernetes, it does not adequately virtualize all of the C group settings, right? Because if you look at it, there are multiple ways in which a container could query for how much memory it has access to, how many CPUs it has access to, what disks it has access to, and all that, right? Docker actually handles many of the cases, I mean, many of the sysfs and procfs and all that, but not everything. And when we were running, for example, HANA, or when you are running things like Kudu of Cloudera, right? We were seeing that, the JVM, for example, right, it essentially starts seeing the entire host memory, right? Even though you're capped the memory for the container, right? Because it's the off-heap memory is essentially exposed to the sysinfo system call, not through the sysfs and procfs system calls or the interfaces, right? So you got to address that. I mean, you got to virtualize all of the C groups to a container so that the container and the app running within the container actually sees exactly what has been allocated to it. Right? So that's one. The second one is around C group settings for IO management. So the BLK IO C group setting is actually practically useless for, I mean, actually it's not really exposed to Kubernetes, but even if it were, it's practically useless to do capping of storage IOPS per pod. And the reason for that is the BLK IO C group setting is on a per volume basis, right? And a pod could have multiple volumes at the same time, right? I mean, if you look at, I mean, any of the complex database workloads, right? You could essentially have multiple data files, each sitting on a different volume and things like that, right? Now, you really want to cap your IOPS across all those volumes, right? Which essentially makes your BLK IO-based C group setting useless, right? For doing noisy neighbor management. And the final one is around raw disk access. Again, complex workloads do not want to rely on ext3 or ext4 or XFS. They would want to get a raw block device and then write to it directly. Things like MapR, Oracle RAC, for example. Now, the way the WWNs for those devices is managed is kind of broken because when the pod restarts and all that, the WWNs are not correctly assigned. And as a result, the application has to change to go and discover whether it's actually the previous volume is bound to the same WWN that it understands and things like that. So those are the 4 CRI challenges that need to be overcome. By the way, all of these can be overcome. Just kind of highlighting what are the challenges first. Right? I'll talk about how to overcome them in subsequent slides, but let's just go through the challenges first. Now, finally, Kubernetes. So we talked about CSI, we talked about CNI, we talked about CRI. What are the KRS challenges, right? I mean, in fact, it would feel that stateful sets, persistent volume claims, volumes, and all those should typically address most of the concerns, right? But a few things that I'd like to call out here, right? Which I already mentioned earlier. We are talking about workloads that predate Docker and Kubernetes, right? So many built-in assumptions around how they are designed. For example, not everything is designed as a microservice, right? Not everything can be stopped and restarted very easily. There is a restart crash recovery phase that things need to go to, right? So which means that you just cannot kill a pod and restart it very easily. There's a cost associated with that. Scaling is slightly different. You just don't use the replica set or stateful set based scaling by throwing another pod at it and leaving it to the workload to figure out, right, how to load balance across those pods. Right? So there is usually built into the application or the workload itself is how the ring of all those pods is maintained and all that stuff. Right? So it's slightly difficult to take a completely microservices oriented architecture and then fit it or fit complex workloads onto that architecture, right? And that's where, of course, operators started to come in. I think operators are a very good framework. It's an awesome framework. So the question is, wouldn't operators solve this problem? And the answer is, yeah, to a certain extent, it does. And then operators are custom logic that you would write that would essentially overcome some of the provisioning and scaling challenges that are natively available through Kubernetes primitives, right? You essentially put workload-specific logic into a workload-specific operator, right? But again, the operator still is just handling the workload-specific challenges. The CNI, CSI, CRI challenges still reside outside the logic of an operator. Those still need to be resolved, right? To be able to create an operator that works seamlessly with all these workloads. The next one is around lifecycle management. Unlike stateless workloads, stateful workloads, when you start, they have a long journey. They usually are running for years, months, years, quarters, which means that you have to handle lifecycle management like snapshots, clones, backups, and restores. Now, all of that, staying inside the operator is not feasible. You really need to rely on outside things. For example, to take snapshots, you have to rely on storage level primitives to take a snapshot, right? When you're trying to create backups, you might have to rely on a backup tool to do that backup and stuff like that, right? So it cannot completely be solved through an operator. And the last one I'd like to call out is operators are great for individual workloads, but if you create a multi-tier workload, how do you handle the lifecycle management of a multi-tier app? Are you going to create a super operator that spans multiple operators, or how do you do that, right? So that's something that it's a very interesting problem, right? It's something that needs to be addressed too, right? So I see that there's a question, why do customers want to run big data databases on Kubernetes? It's a very good question. So think about it this way, right? In any pipeline or in any multi-app, which is stateless, somewhere along that pipeline is a database or a big data platform where data is, right? Essentially, compute-only workloads either rely on data coming in over the network, or they rely on data that is sitting out in a database or a big data platform. I mean, they don't exist in isolation, just doing computing over nothing, right? Now, clearly, Kubernetes has demonstrated the agility benefits of putting all the compute-only stateless workloads, right, on Kubernetes. Now, the question is, wouldn't it be awesome if you can bring the same level of deployment as well as lifecycle management agility to databases and the big data platforms on which these stateless workloads rely on? Right? If you can do that, then essentially you can spin up entire stacks and entire multi-tier stacks, including stateful workloads, in one shot. Right? You can lifecycle manage them very easily and all that. So essentially, it calls out for the agility benefits that you would see if you can bring the stateful workloads or complex stateful workloads also into the Kubernetes fold. Okay, I hope I answered that question that was posted on the chat window. All right, now moving on, let's talk about. I just want to kind of summarize this whole thing by looking at, if you were to put all of this together, if it's like assembling this nice, you have all these great parts to assemble a car, and you put all of these parts together, right? And you expect that you're going to see a car that looks like this, and in the end, you actually see something like this, right? It's a nightmare to manage, maintain, troubleshoot, and stuff like that. Okay. Now, how do you go about addressing or thinking about solutions for this? Okay. So before we jump into the architectural underpinnings for the solution, right? Let's look at it from a slightly higher level view, okay? Instead of just looking at infrastructure components and all that. Let's reframe our thinking. So if you notice, at the end of the day, developers or DevOps people, they rely on applications, right? And applications rely on infrastructure. So in a way, infrastructure exists to serve the needs of an application, which in turn exists to serve the needs of a user. Now, when you look at the solution space that we have been essentially, as all the vendors, right? talk about are along the lines of, let's start solving it from infrastructure upwards into users, which means that, oh, in order to deploy something, oh, let's worry about first creating stateful sets and deployment plans and PVs, PVCs, and all that stuff, right? But what is the net goal? I mean, if you look at what is the business objective, right? To a line of business user, they just want to go run a kubectl command or a Helm install or whatever it is, and they just want to bring up a workload, right? Without having to write any of these things. So what you really need to do is think about the problem from the top down. If there's a way in which you can express the app's needs and then think about it like a super operator that translates those needs into the appropriate CNI, CSI, Kubernetes, all those things, right? Then you essentially can provide the agility that one would really want for both deployment as well as the lifecycle management of these complex workloads. Okay, so this is the framing, right? Essentially, what I wanted to highlight is we need to start looking at the problem from an app downwards instead of looking at it from infrastructure components upwards, right? And when I say infrastructure components, I put things like stateful sets, replica sets, deployments, PVCs, all that into infrastructure components. Okay, so now let's start digging a little deeper into what would be an ideal architecture, right? The first thing, of course, is Kubernetes, and it's no brainer there. Now, because you're targeting data-centric workloads, you need to have a very strong storage story here. Now, again, what does this very strong storage story mean, right? So obviously, you need to have disk management. Obviously, you need to have volume management and all that. CSI is a great framework to provide and allocate those volumes. But beyond that, what you really need to simplify operations and to ensure that you're meeting the performance SLAs and all that is your storage stack to understand the notion of an application. So what does it mean to understand the notion of an application and what are the benefits, right? So when a storage stack understands an application, what I mean by that is the storage stack provides primitives which allow the top layers to go and program it and tell that, okay, these are the different volumes I need. These are the different SLA characteristics of the volumes. And this is the deployment hierarchy / fault domain constraint that the application puts on those volumes, right? See, in a way, the storage stack should understand the topology and the performance characteristics of your application at a programmatic level. That's a very key thing, right? The second thing is once you have that, what is the benefit, right? The benefit is once it understands this, you can truly now start doing application consistent data management, things like an application consistent snapshot. Because all you can now do is, okay, I want to snapshot this particular app, and the storage stack knows that, okay, this particular app is composed of these different LUNs that are spread across these different volumes that are spread across these different disks on these nodes, right? And then you can create a consistency group across all of them, and then you can truly create an app consistent snapshot. In a similar way, it can also truly do an app-aware quality of service management. Instead of doing it at a per volume basis, it can essentially do QoS management for IOPS for an entire app or partitions of an app. So that's a very key ingredient for solving this problem, right? The next one is around networking. I already talked about CNI that needs to be extended for providing persistent IP addresses. So you need to have an IPAM module that closely works with CNI so that when IP addresses are allocated, you can annotate your pods and say that, okay, these pods require a persistency of IP address when they're relocated. So together with CNI and IPAM management, that guarantee is met, right? So that's one. The other thing I'd not highlight here is how reverse DNS needs to be also handled. I think with Core DNS, the latest version of Core DNS that is fixed, but sometimes the reverse DNS for apps does not resolve it correctly, and things like Cloudera sometimes do not come up easily, right? That's not addressed. So net, these are the three infrastructure level components. But what I said earlier is we have as participant of this community, right, of this ecosystem, I think it's our responsibility to drive simplicity for the end consumers or developers or DevOps folks, right? So just these three components by themselves does not meet that goal, right? What you really need for simplicity is a top level view, which essentially exposes primitives. It's almost like you take a super operator kind of a design pattern, right, if you will, which exposes primitives that single click or a single REST API based way of snapshotting or cloning and upgrading and backing up and deploying workloads. And what this thing does is it translates any calls that are made at the top into the appropriate Kubernetes calls, say storage call, networking call, and so on, right? So again, for the more technically inclined audience, and this is just still a block diagram, maybe I'll go a little deeper, right? Now I'm actually sharing a little bit of how we have solved this problem. There might be other solutions, but how we have solved this problem, I'm going to share with you. So this is a behind the scenes architecture. Again, this is a Robin IO solution. So here you can see the traditional master nodes and worker nodes of Kubernetes. The yellow-orange components are stock Kubernetes components, obviously unmodified. We are a CNCF certified software, right? So everything is unmodified here. But all the remaining blue components is what you really need to do. And this is where the Robin components are. All the remaining blue components is what you need to essentially overcome the CNI, CSI, CRI, K8S, and operator challenges that I already outlined earlier, right? So, for example, there is on the right-hand side, you see a CRI switcher that you have built that allows during pod definition and all that, you could basically choose different types of CRIs, right? They can coexist at the same time. For example, Oracle Rack by the company Oracle is supported only on LXC containers. So we are able to run LXC alongside Docker on Kubernetes. The other one is around Docker extended. This is nothing but enabling certain options within Docker so that you can, process the state changes made to the root file system across pod relocations and all that, right? So that, as well as things like GPU based things, right? When you're using NVIDIA's Docker driver and all that, that happens for Docker extended CRI. CSI, of course, is our storage stack, is an enterprise grade storage stack. And there's a CNI switcher that allows you to pick between Calico as well as OVS. And this is the area where we have done some innovations around providing multiple next to the same pod and things like that, right? Again, on top of all of that, on the left-hand side, we have this data app super operator that generalizes, so you don't have to write an operator for each and every different workload. It just provides all the primitives so that you can bring in many workloads, and that's the way we were able to bring in Cloudera, Hortonworks, Splunk, Oracle Racks, Kafka, Elasticsearch, what have you, SAP HANA, and all those workloads onto Kubernetes. So there's also there's a daemon set that runs on every node, and what this does is it basically takes and in fact I have some demos, but I think it's not complete without really showing you giving you a feel for how it actually looks and functions, right? So I do have demos, but before we get into the demo, so you can see on the left-hand side, there's this component called Robin. It's a tooling, which is a CLI, REST, as well as a UI-based tooling that we have provided that simplifies deployment of these workloads to an extent that the developers does not have to write YAML files and all that stuff. And as you'll see in the next demo that I show you, it is the one that takes the needs of your application and it translates them into the appropriate calls around the CNI, CRI, CNI, as well as Kubernetes by running it through a plan manager and feeding it through an overlay scheduler on top of K8S scheduler. So in all this diagram here, you see that we have not really modified a single line of Kubernetes code, but we use the extensibility features that are built in, right, to get to this level of sophistication. Now, as I said, right, I think it's important to kind of get a feel for how it looks because this is real, right? So you want to really get to feel it, right? So I'm just going to, I have about 3 slides on just few demos, so that will kind of highlight things. So here is a dashboard where all these workloads are running on Kubernetes. Let's say I want to deploy Hortonworks, one of the very most complex workloads, because Hortonworks is not just your HDFS and all that. It has so many different services, right? Each of the services has so many different quirks around Kerberos integration, Sentry, and whatnot, right? So you have to simplify how you define or how you compose your Hortonworks deployment with all those services, right? So what Robin allows you to do is create a YAML file that just talks about, okay, these are the different services within Hortonworks, right? So let's just see a demo. So let's say somebody clicks on Hortonworks here, right, on this icon. So we render a screen that looks like this. On this screen, they'll be able to go and toggle and pick whatever services of interest to them, right? Whether they want Kafka with Hortonworks, they want Hive, they want Knox and Atlas and whatnot. Once they pick that, they can just go and say, okay, what is the scale at which you'd like to deploy each of these services? What are the compute resources? If you have GPU needs, what are the GPU needs, right? What are the storage needs that this particular workload has, right? You can click on the wrench, you can also go and specify performance SLAs, isolation guarantees, data protection policies, right? Whether it's replicated or it is encrypted or it's compressed and all that stuff. But beyond all these workloads also, as I said earlier, right, have fault domain constraints built into them. They have data locality constraints built into them. So you should be able to go and toggle and say, you know what, I want data locality, I want anti-affinity across these services, not just at the pod level, but also at the storage level, and just toggle it. And then this provision, and then we basically take, in the previous screen I showed you this plan manager, right? It takes this, it generates a plan, then it emits the appropriate pods, the PVCs, PVC specs, services, all of that stuff. It emits all of that thing. It talks to the Robin storage layer, which again, as I said, app aware, and it programmatically goes and provisions these volumes, associates each volume into a hierarchy of how it kind of maps into the entire app and all that, right? So net, within a minute, within minutes, you're able to deploy very large deployments of complex workloads. So when I say minutes, right? Let me give you an example, right? So we have demonstrated at last Strata a 500 node Cloudera cluster running full blown, right? A production quality 500 node Cloudera cluster, about 1.4 petabytes deployed in 44 minutes on Kubernetes, right? So that is the power of bringing these workloads onto Kubernetes, right? Using a platform like this. So beyond deployment, as I said, deployment is one challenge. You got to worry about data management. So let me kind of showcase a few data management and how we can up-level them from just storage level data management into an entire app level data management. Here we have a Cassandra cluster running. It's a 10 partition Cassandra cluster, 2 seats, 2 members. Let's say somebody would like to snapshot this. All they have to do is go to actions and create snapshot, give it a name, and then click snapshot, right? Now, nobody has to go and specify what storage volumes need to be snapshotted. How do you snapshot that and all that? Because this component understands that, okay, there are 10 partitions here or 10 components, 10 pods here, each pod having a certain number of volumes. This is the consistency group. And within seconds, it can snapshot not just the data volumes, but also snapshot the entire application metadata, right? The pod specs, the PVCs, services, all of that stuff. And it can create a checkpoint of your entire app, right? And even if the app's topology changes over time, you can just preserve all those changes very easily, right? In this app level snapshot. What happens when you have these snapshots, right? Obviously, you can do time travel like you do with your Mac, right? You can time travel across different application snapshots. If, let's say, for example, if QA says that, hey, listen, I found a bug in such and such version, and the dev says, oh, you know what, I'd like to go back and see if the bug also existed when the app had 3 partitions, right? Click of a button, you can essentially go back to that. That's one obvious benefit. The next obvious benefit is around creating instant clones, right? You basically go and say, this Cassandra app, as of 2 weeks ago, I want to create a quick clone, right? Now, you don't have to go and specify the pods. You don't have to go and say, persistent volume claim, the source is this snapshot content, none of that stuff. You just say, I want to clone, right? And then you're going to translate this into the appropriate calls. You have to go and tell the storage stack that, okay, this is a thin clone that's happening, so you don't have to copy the entire data out, take a referential copy, right? On the networking side, you have to provide new IP addresses and all that stuff, right? It's all automated. It happens in a matter of seconds, right? So that is clone. I mean, I could show you a few more demos, but I think in the interest of a lot of questions that are coming up, maybe I will pause here and I'll take any questions.
Awesome. Thank you so much, Partha. Great presentation. We do have some time for questions, so 17 minutes. If you have more questions, feel free to drop it into the Q&A section on the bottom of your screen as well. Otherwise, I will just try to get at least one question answered from everyone that asked now. Let us start with Bruce. So the question is, are you running virtual machines within Kubernetes to solve any of the proof points that you've built, such as the Oracle rack instances? Or are you solely relying on native container capabilities?
Fantastic question. So for the example that I showed you, the 400 Oracle rack clusters, it's running entirely on containers, LXC containers specifically. That too because Oracle, the company, only certifies Oracle RAC in LXC containers, not Docker. But the moment they support Docker, we will support that as well.
Awesome. Okay, let's continue to Walid, who's asking that for CSI storage, if I have NFS on all Kubernetes nodes, do I still need GlusterFS, Longhorn, or should I just use the NFS on the worker nodes? If yes, should I use it on the host?
So it's a loaded question, right? Essentially, the question is around, I mean, it's a multi-part one, right? NFS versus GlusterFS and all. So maybe let me generalize the question itself, right? So if your workload requires file-based storage, right, which is typically not databases and all that, but several other workloads, then you have multiple choices that you can make, right? Obviously, NFS is one. NFS is, of course, it's a protocol. So you have to go with vendors who are providing the protocol access, right? So GlusterFS is a distributed file system, right? In addition to its own proprietary protocol, it also supports NFS. So it's an implementation of NFS, if you think about it. So if your question is, do I choose between, let me read the, so for CSI storage, if I have NFS on all K8s nodes, do I still need GlusterFS? I'm assuming that when you say I have NFS on all client nodes, you already have some other NFS storage provider. So if you have that, you don't need GlusterFS, unless I'm misunderstanding the question.
Okay, so if that didn't answer the question, maybe just ask again.
Or you can also email me at this thing later if you.
Perfect. So let's continue to Daniel for now, which is asking, DNS or external IPAMs cannot solve the persistent IP issue?
DNS or IPAM. Yeah, IPAM does. Yeah. So you have to drop, exactly, that's a good point. So when you want persistent IP addresses, IPAM is the way to go. You have to provide an IPAM module. The standard Flannel or Calico does not provide that. All I wanted to call out is that that's a challenge and we need to address that by dropping an IPAM.
Okay, great. Then we have Andrew who's asking, does this require access to and control over master nodes? Is this compatible with managed solutions like AWS, EKS, or the Azure Kubernetes Service or Google Container Engine?
So we don't need access to the master node. So you can have the master nodes be a completely different control plane. We register with the master nodes. We have our own service account and all that. So that's the first part of the question. The second question is, does it work with managed solutions? We are going to be announcing pretty soon. Right now, it doesn't work, but managed services. But we are announcing in April timeframe an integration with managed services as well. So you can choose your own Kubernetes distribution.
Okay, awesome. So we have Bruce who is asking if you have looked at Wirtlet and the CRI proxy.
Yes, we have. In fact, Wirtlet is a pretty cool project. In fact, that's one way to essentially run KVMs alongside Docker or things like that. So we have looked at both of them. I think it's a good solution. Yes. So I mean, just for the other folks who may not be familiar with this, is if you would like to run virtual machines alongside your Docker containers, there are multiple projects for that. So Wirtlet is one of them. So yes, we have looked at them.
Okay, maybe a short one. So Sylvie is asking if the product is open source.
No, it's not an open source product. It's a commercial product.
Okay, so we have Binu who wants to know, do you support on-premise clusters?
Yes. We support on-premises running on bare metal or within virtual machines, as well as we support AWS and GCP and Azure. Because it's a software-only solution, so it works anywhere.
Okay, Thirumalai, I hope that was spelled correctly, is asking, how can we implement Confluent Kafka Mirror Maker for metadata schema for different synchronization without any delay for automation deployment?
That's a very good question. We do have customers who are running Confluent Kafka, but I think this is a longer, more technically involved answer. So maybe if you can shoot me an email at this email address, I can respond back.
Perfect. So that's one question from anyone. So let's start with the ones that already had the question. So Bruce got another question. do you find that the storage performance is equivalent within a containerized environment versus a decomposed virtualized environment? Or is there a benefit in the performance for one infrastructure choice over another?
Yeah, so the performance is equivalent because if you notice, containers really do not interfere with IOs at all, right? Because if you think about it, right, at a fundamental data structure level, a container is an isolation technology, right? It is not a virtualization technology. So it really does not get into the way of how your IOs are managed. And I mean, the fact that we run these workloads which are very transactional, right? Whether it's Oracle RAC and all that, all our customers actually evaluate us for our performance and how close we are to the native disk performance, and it is perfectly achievable using containers.
Very good. So the next two sound like you can compare them, which is which service mesh do you prefer, and does service mesh actually help you to resolve networking and storage locality issues described previously?
No, it doesn't. So we don't have a preference for a service mesh because clearly that's not something that, I mean, that is complementary to the solution, right? It is not like it's a required thing. So we don't prefer anything. Customers use many things, whether it is Tio, Envoy, whatever it is, they get to pick whatever they want. The second part is, does it help? Not really. I mean, there are orthogonal problems from that perspective, right? How data locality is managed is actually a storage orchestration problem that that goes beyond the scope of service mesh. Right?
Perfect. So Walid is asking regarding CRI, do you think I assume, we will see more CRI-O in Kubernetes than Docker?
I think we will. I think the industry seems to be moving in that direction. I don't know if we'll see more of it or not. There is also a chicken and egg problem. I mean, I think there's a lot of vendors who are shipping their containers as Docker containers right now, right? So, I mean, you have to see how the ecosystem evolves around this. But I think CRI-O is also here to stay. And I don't know if there will be a time when it will overtake Docker, but maybe it will coexist in the short term. And over time, whichever wins, whichever has the more broader vendor support, I think will win.
Okay, great. So we see machine learning data science trends to run inside containers, and to make them resilient, they require Kubernetes. Are there platforms to make it user-friendly? Another question by Walid.
So if I understand the question, it is running data science. Can you repeat?
Yeah, sure. So we see machine learning data science trends to run inside containers and to make them resilient. They require Kubernetes. Are there platforms to make it user-friendly?
Yeah, so obviously there could be managed services platform that makes it user-friendly, right? But I can answer it from the perspective of Robin. So we do support machine learning workloads such as, distributed TensorFlow, Caffe, Theano, those kind of toolkits, the notebooks, Jupyter notebooks and all that stuff. So clearly it can be made a lot user-friendly because, again, when you're deploying all these things, the fact that you have to stitch the NVIDIA Docker as your CRI, the fact that you have to go and give a certain number of GPU cores to your workload, and if you want to get your training data done sooner, you would like to scale your GPUs up or take them away when you don't need them. All that is an operational challenge, right? And all of that, typically a data scientist will not neither know nor care about looking at, right? They are just interested in building their models and working at, the math level of things, right? They don't want to be worried about GPU allocation and scaling and stuff like that, or scaling more TensorFlow worker nodes. So clearly, we do make that a lot simpler using our way of elevating the entire experience from infrastructure into applications like the demos that I showed you.
Perfect. So we have 3 more questions and more than enough time. So if anyone else has another question, feel free to drop it into the Q&A section. Otherwise, there is Daniel who's asking if the super operator is an extensible framework.
So it is. The super operator is an extensible framework, although it depends on what you mean by extensibility. So it will be good if you can forward me an email with specific questions. But yes, it is extensible in the extent that with the single super operator, we are able to onboard all the workloads that I just talked about, right, including Oracle and HANA and all that.
Okay, so Daniel again is asking, what features do you provide when you say multi-tenancy?
Okay, very good question. So a couple of things here, right? Maybe I should have highlighted that in the slide itself. So there are different levels of isolation and multi-tenancy capabilities in place here, because you're talking about applications that have data, and that data could have sensitive information, right? So the policies that our customers typically ask us to enable on this platform is the following. Number one is hardware level isolation. So we have to guarantee them that there are certain workloads that are hardware isolated, right? So it essentially means that there's one database that can run only on these set of nodes, and another database can run only in the other set of nodes, right? That's one way of looking at it. Then the other way of looking at it is at the resource and quota level, how much you're giving, not just for CPUs and memory, which is again mostly solved through resource limits and all that, but also at the storage IOPS level, right? So that's the second one. Now, the third level of multi-tenancy, which kind of becomes very interesting, is in an enterprise account, right? Let's say a user John, right? User John deploys his own database. Now there would be another user, let's say Sally, right? And Sally also deploys her database, right? Now, if you look at it from a purely Kubernetes namespace perspective, let's say both of them belong to the same group, right? Same dev group, let us say. If you put them in the same namespace, then both of them can see each other's databases. So in an enterprise, that's a big no-no, right? So they essentially say that, okay, whatever databases that John spins up, only John should be able to see. Whatever Sally spins up, only Sally should be able to see. Whatever John and Sally spin up, the tenant admin should be able to see, right? That is the way an enterprise consumes things, right? So what we had to do is we had to build a RBAC as well as a multi-tenancy on top of Kubernetes RBAC mechanisms, so that we can provide that namespace level isolations and all that to meet this particular enterprise need. Again, happy to answer if you have more questions on this. Just shoot me an email at partha@robin.io.
Great. So last but not least, there is Binu who is asking, how do you handle transparent encryption with outside key management?
It's a great question. So our storage stack itself has encryption built in. So when you are deploying your workload, you can say, okay, these are the volumes I would like to do data at rest encryption. So what we do is that we generate a 40-byte key per volume, and that key is then encrypted again by an external key management super key, right, or a master key, which sits in an external KMS the software somewhere else outside. And as a result, the workload itself does not have to worry about where to keep the keys and how to do the encryption and all that. You just have to toggle and say, I want encryption for this volume, and it is all handled. At a cluster level, you have to register an external KMS. I hope I answered it.
Thank you so much. That's all we have. So thanks for joining us today. Also to all the participants who didn't have any questions. The webinar recording and slides, we will upload them later today. So yeah, have an eye for them. We will also email you a link. They will be on the CNCF website. So we look forward to seeing you again at future CNCF webinars. And yeah, have a great day. Thank you so much. And if you have more questions, feel also free to email Partha. Thanks.
Thank you, everyone.